Hello, this is Mike here with another validation model. This is the 12th validation model that I'm doing for Autodesk Inventor Nastran. You can see that we are going to work out of 2022. If you're using a slightly older version, that should be okay. I don't think I'm going to do anything here that would require the latest version. So the origin of the model, it's a flat rectangular plate. The edge is fixed and uniform pressure, and it does come from Rourke and Young. You can find it in the 5th edition, page 392, table 26, case 8a. So again, we have a flat rectangular plate, all edges fixed, uniform pressure load. We're going to analyze it for the maximum stress. The length of this plate is 12 inch by 6 inches wide. Thickness of it is 0.25 inches, and it has a pressure of 100 psi. The material properties will include a Poisson's ratio of 0.3, Young's modulus of 30e6, and because of the geometry being symmetric, the constraints being symmetric, the loading being symmetric, we will do a quarter symmetry model just because it's the most efficient way to do it. And then we're going to try and target the theoretical max value of 28,650. So let's go ahead and get started. Again, here in Inventor, what I'm going to do is just go ahead and start with a part, and that should make it nice and easy. And let me move this Excel sheet off to the side. For this one, since it is a shell model, I'm just going to start with a sketch, and we're going to sketch on the XY plane. And then we're going to go ahead and add a rectangle in, and I'll start the rectangle at the origin and begin to pull it out. And again, remember it was a 12 inch by 6 inch, so since we're going to do a quarter symmetry, we'll make ours 6, and then I'm going to hit tab and we'll do 3. So a 6 by 3 rectangle, and if I zoom out, there we go. So 6 inch this way, 3 inch this way, so you can see it's a quarter symmetry model. You can imagine if you mirror this over along the y-axis and then mirror those two portions along the x-axis or about the x-axis, then we would have the full 12 inch by 6 inch model. But again, we can take advantage of symmetry in this case. So the only other thing that we need to do here within the Inventor environment, I'm going to go ahead and hit finish sketch, and since we're going to do shells, we can do shells with surface geometry. So I'm going to go ahead and use the patch command, and we'll patch that enclosed region, and we'll say OK. So there's our surface model. It's just a flat rectangular surface, and that way when we get into the Nastran environment, we can assign shells to that. You certainly could draw something that is a 3D model, right? We could make this 6 inches long, 3 inches tall, make it a quarter inch thick, and then when we get into the Nastran environment, we can use the tools there to collapse it down to its mid-surface. But that's really just creating, in this case, since we're starting from scratch, some extra work for ourselves. But please be aware, and I've showed it in some other videos in Nastran when we're working with shells, that if somebody hands you a model and it's a thin, solid body, you certainly can collapse it down to the mid-surface if you ultimately want to analyze using shell elements. But again, since we're starting from scratch, may as well just make it out of surface geometry. Quick way for us to then assign the shell elements. Let's go ahead to Environments, and off the Environments tab, that's where we can access our Autodesk Inventor Nastran. Now, when we come into Nastran, because this is surface geometry, it does not automatically create an idealization for us. If you've watched some other ones with solids, you know that it automatically adds an idealization. It sets the element type to solid, so that way whenever you generate the mesh, it's of course creating those solid elements. But again, because we have just a surface, we need to create that idealization. No big deal. Let's go ahead and click on Idealization, and in here what we can do is tell it that we don't want solid elements. We're going to utilize a shell element for this. I've also done some prior videos using line elements. For those, you just draw a sketch line in Nastran. When you bring it in, you can then define them as being beam elements, for instance. For this one, we want to use shells, and we are going to define a thickness here. That's the upper right hand corner, T equals. We're going to make that 0.25 inch. Now, had we come in with a solid model that was 6 inch by 3 inch by 1/4 inch thick, and we used the tools here, the offset surfaces, to collapse it down to the mid surface, this field would automatically get filled out. It would extract what that thickness is, so it's able to determine what it is when it does the operation. You can certainly modify it too, so you can change it, and that's one of the great things about using shells. If you run an analysis and you look at the stresses and you go, wow, those stresses are really, really low, my safety factor is massive, well, then you can go quickly and say, well, what happens if we make it out of a thinner material? Maybe save yourself and the company some costs if you get away with a thinner material. Sometimes the inverse happens. You analyze it, find that your stresses are quite high, and then you can take a look very quickly at what happens if we change the thickness to maybe something a little bit more substantial. All right, coming over here to the left-hand side, we are going to change our material, so we can just go ahead and click on that box right there, and we're going to give it a Poisson's ratio of 0.3. We could certainly select the material, right? I could go in here and I could say that I want to select the material, and then we can choose from the various libraries. That I generally, if it's undefined, I generally come down and I take a steel, ASTM A36. That would be fine. So there's the 0.3. If we want to change the modulus, we can do that. Just type in a new value. So we'll say OK to that. The other thing on this screen, or one of the other things, next to last thing we'll discuss, right here is the color. So that would be the color for the mesh. So if you had multiple surface bodies, for instance, within your setup here, and maybe you were going to define them with different thicknesses. Maybe you have some parts that are 1/4 inch thick, some parts that are, I don't know, maybe 3/4 inch thick or 3/8. You could set up different idealizations and add those different surface geometries to different idealizations. So that way you could define the different thicknesses for those different idealizations. In that case, you might want to change the color of each. So that way, when you're looking at the assembly, your FEA assembly, you could very quickly go, okay, there's a green mesh part, there's a blue mesh part, there's a red mesh part. I know what these different colors mean, they're the different thicknesses, and I've assigned the different thicknesses to those different regions appropriately. Likewise, you could change the material for each one of those different regions. For us, we only have a single surface region here, so it's all going to be the same thickness and same material. Let's go ahead and change the color. I'm a big fan of blue. So okay. And then again, there's the associated geometry. So if you had different surfaces you wanted to assign to different thicknesses, you could check that box and then select the different regions to add them in here. We don't need to do that because, again, it's all going to be the same thickness, same material. Lastly, below that, you can define whether you want to have quad shell elements or triangular shell elements. Quads would be great for this. We'll just go ahead and say OK to that. At this point, all we have to do is generate the mesh. So let's go ahead and generate the mesh. I'm going to go ahead and take the default mesh that it gives me. We'll take a look at our results and see how close we are, and if we need to go finer. In this case, because we know what value we're trying to hit, we could do that if we need to. We'll go into mesh settings, and just to show you, we can see that it took a mesh size of about 0.25, a little bit larger than that. And we are going to run parabolic elements here. We'll say OK. So let's go ahead and set up our loads and constraints. This top edge here and this edge right here are parts of the outer perimeter, right? Our 6 inch and 3 inch edge, really, 1/4 of the 12 inch by 6 inch. And the setup of this model says that the outside is to be, or the perimeter is to be fully fixed. So we'll go constraints, and I'm going to assign a name to this. You don't have to, but it helps to keep my model tree a little bit organized. So we'll do fixed, and then under select entities, we're going to go ahead and select this edge and this edge. Just left click, and I can see those two edges are there. Currently all of my translations and rotations are checked, meaning they will be constrained against translation in XYZ and rotation XYZ. We can change the color of those symbols. We can change the size of the constraint symbols and how many constraint symbols get applied along that edge if we'd like. All adjustable. Let's go ahead and say OK. So without changing that, you can say I get kind of these green constraints and one of each along each of the edges. Right? Okay. And you can see that adds to the model tree over here. So it tells me that I have a fixed constraint, or I should say I gave that constraint a name and called it fixed. As far as what the glyphs mean, I think I've explained this in some other videos, but the single arrowhead is a constraint against translation. So here we have a single constraint against translation, and then if you look in the vector direction, looking at the mini-axis, it's in the Z. So I can look at that constraint and say, okay, I know I have Z constrained there, and then the double arrow, translation Z, the double arrow are your rotations. So we also know that we've constrained against rotation in Z. And then likewise this one, single arrowhead along the x-axis and then a double arrowhead along the x. So both translation and rotation about x. So just a little bit there about what these constraint glyphs mean. Let's go ahead and do the other two constraints. This edge here, the vector that is perpendicular to that edge is the x, so that is the symmetry that I want to assign to that edge. So let's go ahead and do constraint, and again we'll name it. Let's say we call it xsim, and then down here on the lower right hand side we can choose an x symmetry, and you can see what it's going to fix: translation x and then the two in-plane rotations ry and rz. Let's go ahead and say OK. Whoops, I need to select that entity. Alright, there we go. So there's the translation, single arrowhead, translation x, and then I have a rotation here aligned with the z, so that's rotation about z, and then rotation about y is constrained. And again, because we named that constraint, you can see that it's added itself to the model tree. Last constraint, that would be this edge here. Axis perpendicular is y, so we are going to call that y symmetry. Select that edge and select a y symmetry. Alright, there we go. So that's everything for constraints. And then lastly would be our load. The load for us was defined as a pressure. So let's go ahead and change from the pull down menu. Type of load is a pressure, and it is 100 psi. You ask yourself if you need to adjust that for the fact that we did a quarter model. You do not, technically, right? Because the fact that the total load that is applied, since we're using a pressure is what? The force over an area. We have 1/4 of the area, so it automatically, if you will, it's self-adjusting, really. So we can use the same amount of pressure that was defined for us in the problem description. Let's go ahead and say OK to that, and there's the arrow indicating that we have pressure applied. And then at that point we can go ahead and run this simulation. Let's go ahead and press run. I need to assign a name to it. I guess we're down to 12, right? V12 demo. We'll save that. Alright, and at that point it should run the analysis, and this will run pretty quick. Not a whole lot of elements, not a whole lot of nodes. There we go. Alright, and there we are for our results. And what we want to take a look at is a tensor in the y direction. So up top here we can change, whether we're looking at displacements, rotation, or stresses. We're going to take a look at stress, and then we're going to take a look at y normal. And there we go. There's our value, 2,839, it looks like. If you want to get really, well, the max probe is at that location. But if you want, you can go into nodes, select query display, and then as you move over top of nodes, that will report the value for you at those different nodes. So 2,839 is what we're looking at. We go ahead and type in that. Oh, yeah, did I read that wrong? Yeah, it's e to the fourth. So 28,390. 28,390. Type that into our spreadsheet, hit enter, And there you can see that the percent difference from our theoretical solution is less than 1%. So I would say that is quite good agreement. And I hope you learned something useful in this particular demo. Thanks for watching. You have a great day.